Hi, welcome. So if you don't know me, my name is Bing Yang Ho. I'll be your physics instructor for Physics 2 this semester. If you haven't done so, go ahead and actually check on the syllabus before you actually continue this lecture or watching this lecture. So um, this is a Physics 2. It's a continuous from the Physics 1 that we had last semester. From this semester on, we'll actually deliver the um, lectures in the flipped classroom mode, which means I will record videos for lectures prior to the classroom. You guys are going to actually watch the videos before you come into the class. Okay, so check on the details of the in the syllabus or um, meet with me, and then we can talk about more of the details. So for the first lecture that we do actually on the day we will have our first lecture. Okay, so this semester we'll talk about topics over thermodynamics, electromagnetic, um, electricity and magnetism, and then wave and optics. Those are the main topics. Okay, so we'll jump in for the first topic on thermodynamics. We'll start with temperature, um, and then expansion for today. Okay. So you guys all know temperature. So um, we here in the United States we use Kelvin or use Fahrenheit for the unit for the temperature, but actually the SI unit for the temperature is not Celsius nor Fahrenheit. So Celsius you guys are pretty much familiar with in your other science classes, but actually SI unit for the temperature in this class or in science in general is Kelvin. We use K for the symbol. The physical definition for temperature is listed here. The high values of something with hot object and low value of it with cold object is called temperature. This is the physical um, definition of it. When we measure temperature, we use thermometers. So there are different forms of thermometers. So the old-fashioned ones here, like if you have a thermostat at home or style, you'll see that there's a needle and then there's a scale over there. Or more the physical ones you might have used in chemistry, this type of thermometer over here in the middle. These days at home, we pretty much have digital thermometers. So this is the one they use to check temperature of the body here. Now, in this country, we use Fahrenheit, as I mentioned. So you guys are familiar with that. But in a lot of other countries, people actually are not using Fahrenheit. Most of the countries use actually Celsius. If you travel abroad or um, to any countries, if you travel to any countries, even like just cross the border to Canada or to Mexico, they will use Celsius. Okay, so it's important that we know how to convert actually from Fahrenheit to Celsius. I probably have said this in physics one, but when I was first in the United States, I was used to use Celsius for temperature, but one day the weather forecast says it's going to be something like 85 degrees tomorrow. I was a little bit concerned because 85 in Celsius is very hot, but then it actually it's pretty comfortable temperature or a little bit warm, but not too bad in that case. So there are different temperature scales. How do we know how to convert from one to another? So converting from Fahrenheit to Celsius, and probably sometimes you have to convert into Kelvin scale as well. Okay, so luckily these scales are all linear scales. Okay, so that means for a certain physical event, they might have different values, but they use the same in between two physical events, um, the relation is actually linear. So for example, typically, um, if you look at temperature scales, you can start with a freezing point of water and then using the boil point of water as the two physical events as references. So in Fahrenheit scale, water freezes at 32 degrees, it boils at 212 degrees. Now in Celsius scales, it freezes at 0 degrees Celsius and then it boils at 100 degrees Celsius. In Kelvin scale, it freezes at 273.15 Kelvin and then it boils at 307 is 3.15 Kelvin. So to work on the conversions between any of these two scales, we will look at the two scales, and then we'll find out what's the conversion factors. Here are the formulas to use to convert from one to another. Okay, so let's say let's take a look at the conversion between just the Celsius and Fahrenheit scales. Okay, so water freezes at 0 degrees Celsius. In Fahrenheit, it freezes 32. It boils at 100 degrees Celsius. It boils at 212 Fahrenheit. So that's put up a formula of conversion here. So I'm going to just briefly stop sharing my PowerPoint slide here and then switch my camera. So you can see how we can actually go from one temperature scale to another one. Okay, so let's say the variables here, let's say temperature in Fahrenheit, okay, that's equal to temperature in Celsius with a parameter of A plus B, okay? So we're going to determine what are the A and B parameters here. So then we have a formula of converting temperature from Celsius to Fahrenheit, okay? So the goal is to find A and B here, the two unknowns. And we are using two physical events as our references. So water freezes at 0 degrees Celsius, and also in Fahrenheit, it's at 32 degrees, okay? So we know temperature in Fahrenheit, 32 degrees Fahrenheit is equal to A times temperature in Celsius, 0 degrees Celsius, okay? So, and then the second reference would be the boiling point. So water boils at, again, at two temperatures, 100 degrees Celsius and 212 degrees Fahrenheit. Okay, so in that case, you can write now another equation according to this relationship over here, temperature in Fahrenheit, which in this case is 212 degrees Fahrenheit. That should be equal to a parameter called A times 100 degrees Celsius, and then plus B, and I forgot about B there in the first case, but so 32 degrees Fahrenheit equal to A times 0 degrees Celsius plus the B parameter. So we basically have one equation and two equations, and then we can solve for the two parameters A and B. Okay, for two equations, you can solve for two unknowns here. If we look at these two equations carefully, we will see that because this is 0 here, so then this B will be equal to 32 because this one then goes away. So it gives you directly B is equal to 32 degrees Fahrenheit. Okay. Now we have B already. We can put B into the second equation over here. So then 212 Fahrenheit is equal to A times 100 degrees Celsius plus 32 Fahrenheit. Okay. So you can subtract 32 from both sides of the equation, so minus 32 here and then minus 32 on here. So on this side, you'll get 180 degrees Fahrenheit. That's equal to A times 100 degrees Celsius. Okay, so then you divide both sides by 100 degrees Celsius. Then you get A. It's going to be equal to 180 divided by 100. That will actually give you 1.8, or in fraction, it's 9/5, and it's Fahrenheit degrees over degrees Celsius. Okay, so when you write the units here for Fahrenheit, you do actually a small circle here, and then F for Fahrenheit, and then small circle here, and then C for Celsius. Okay, sometimes people would write, say, in the other way around. They do the symbol first, and then the degrees to the right. But it's a superscript 0 there, or degree C there, because in that case, in handwriting especially, this is used in handwriting, okay? So if you say 1 degree, right, or 10 degree, let's say 10 degree Fahrenheit. So this can be easily misread as 100 degree Fahrenheit, okay? Or you do 10 degrees Celsius, you might be reading it as 100 degrees C in that case. So to avoid that, some people prefer to use this notation or this writing instead of that. But in typing, you can do superscript and then F, superscript for the 0 and then F, and then the same thing for this, okay? So now we have A equal to this, 9/5, and then we have B equal to that guy. So then putting these two numbers back to here, then we can write temperature in Fahrenheit should be equal to A, which is 9/5, and that's in units of degree Fahrenheit over degree Celsius, times temperatures in Celsius plus the B parameter, which is 32 degree Fahrenheit. Okay, so this is then it's your conversion. And a lot of times people will just ignore the units. So they will just use temperature Fahrenheit equal to 9/5 times temperature in Celsius plus 32. Okay, and then at the end, when you have your answer, you can write your units. Okay, at the end there. All right. So let's go back to the PowerPoint slide. Okay. So we have derived the conversion from Celsius to Fahrenheit, which temperature in Fahrenheit, you can also write in this way. So temperature in Fahrenheit is equal to 9/5 temperature in Celsius plus 32, okay? Or you can do it this way, whichever you prefer, that doesn't matter. Now, once we have this, we can now rearrange to get temperature in Celsius. So basically using this one to solve for temperature in Celsius in terms of temperature in Fahrenheit. So you minus both sides by 32, subtract 32 from both sides. So TF minus 32 or 32, sorry, instead of 35, I should say 32, okay? So TF minus 32 and then divided by 9/5, which will flip, give you 5/9. Okay, so a little bit algebra over here, but basically subtract 32 from both sides and then divide both sides by 9/5, which will give you 5/9 to give you that guy. Okay, or you can do the same as we did. You can say TC equal to A times TF and then plus a B. In that way, you can solve for that, and then you'll get exactly the same expression here at the end. Okay. Similarly, you can do derive the conversion from Celsius to Kelvin or Kelvin to Celsius. And then from Fahrenheit to Kelvin, so from Celsius to Kelvin or Kelvin to Celsius is a shift of just 273.15. So they are the same. 1 degree of difference in Kelvin and 1 degree in Celsius, they are the same in that case. So temperature in Celsius plus 273.15 will give you temperature in Kelvin. Or the other way around, temperature in Kelvin minus 273.15 will give you temperature in Celsius, okay? From Fahrenheit to Kelvin, so this is the equation. So it's basically, you are doing Fahrenheit to Celsius first. So this part is from Fahrenheit to Celsius first, and then plus 273.15. Or if you're doing from Fahrenheit to Kelvin, this is the equation, but it's basically on the other way around, sorry, Kelvin to Fahrenheit. So it's basically from Kelvin to Celsius first, and then times that 9/5 right here, and then plus 32, okay? So then you have all the equations to use to convert from one scale to another. All right. So let me put my camera back on. So next, as far as limits is concerned, is there a high limit and low limit for temperature? At this point, we know there's a low limit, but there's not really a high limit of temperature. Okay, so for the low limit of temperature is called the absolute zero temperature. Okay, so and this was this could be demonstrated by using a gas thermometer. Okay, so this is a very old style thermometer here. You have mercury over here, and then you have empty bottle over here. If you label this guy over here on the left-hand side of the U-shaped tube here, and then right side of mercury surface level, if you fix the two levels from the right to the left, then you actually have the fixed pressure inside here. Okay, inside the um, gas here. And now you can change, or you can actually just fix the left side over here, and then you can change the temperature of this water bath or whatever kind of liquid you're using here. So after equilibrium, the gas temperature will be the same as this bath's temperature, liquid bath's temperature, and then you'll see that if this is a flexible tube, so then you can move the right hand side of the tube so to adjust so the level on the mercury on the left will be exactly at this gap, but level on here will be changing according to the temperature. So you can actually figure out what's the temperature of the gas by looking at the surface mercury level on the right here. Okay. So this is how a gas thermometer works. And depending on different types of gas, and you can have different levels here for the same temperature. Okay, so um, it can be shown that in experiment. Let's see if I can hide this guy. Hide him. Okay. All right. So if you have different gases, so as I said, under the same temperature, you have different pressure, and they're all linear here. But if you when you can do experiment here, you can take a few different temperature points and then measure the pressure for different gases. So then at the end, you'll have different slopes of lines here representing different gases. But if you um, extrapolate the lines back to the left, they will all merge at this same point here, which in Celsius is minus 273.15. And on the other end, they do not meet. Okay, so this is where then the absolute zero temperature is. So because the pressure is proportional to temperature, when the pressure is zero here at this point, it's representing that there's no movement of molecules. Okay, so that's the absolute temperature. Okay, so then Kelvin, the zero of Kelvin scale is defined at the absolute zero temperature, which is minus 273.15 degrees Celsius. So then temperature in Celsius plus 273.15 will be temperature in Kelvin. Okay, so we'll take a look at one example before we move on to the next topic here. So here it says normal body temperature for humans is 98.6 Fahrenheit. What's the corresponding temperature in degrees Celsius and in Kelvin? So let's say if you travel abroad and then if you have fever, you go to a doctor, they will probably gonna to tell you your temperature, body temperatures maybe 39 degrees Celsius because every other country uses Celsius. And then you were wondering, am I having a fever? Right? So let's see how we can convert that. Okay. All right. So we are converting temperature, in this case, from Fahrenheit to Celsius. So let me switch my camera again. So from Fahrenheit, in this case to stop sharing so then you can see this better. So we're going to use this equation right above here because we are converting from actually not that one. Sorry about it. We are going from Fahrenheit to Celsius. So we should use the equation of converting from Fahrenheit to Celsius. So to convert from Fahrenheit to Celsius, you do 5/9 actually. You do Fahrenheit minus 32 degrees first, and then times that. Okay, so that's the equation to use. You can look this equation up. And if once you've identified the equation, you plug in the numbers here. So 5/9 and 98.6 minus 32. And you punch these numbers into your calculator. It will tell you it's going to be 37.0 degrees. Okay, so that means if you are 37 Celsius, that's normal. If you are above, you might have fever. If you are below, not too much, then no concern. Okay. And the next question asked in the PowerPoint, if you guys can go back there, it's asking you what's this temperature then in Kelvin. So we already have the temperature in Celsius. So then to convert to Kelvin, it's just temperature in Celsius plus 273.15. Okay, so 37 degrees Celsius plus 273.15. That's going to be 310.15. But you can ignore the 0.15 Kelvin if you want. That should be just fine. Okay. All right. So it's important you know how to convert these temperatures from one to another. All right. Let's go back to the PowerPoint. And switching back. Okay, so next section talks about thermal expansion. Now it's winter here, and a lot of times we see the potholes, which we don't like when we are driving on the road. And in the summer, it's not an issue. Normally, you don't see those during the summer. But this pothole forms because in winter, there's a dramatic temperature change, sometimes in like 20 degrees or even 40 degrees, swimming back and forth within a day or two. So with that, normally materials has this physical property of that is either expand or shrink due to temperature change. So if temperature increases, normally the most materials will expand in length and then or in volume, either way. And then it will shrink if temperature decreases. Okay. Now there's one exception as water. Water at a certain range, it's kind of weird. From 0 to 4 degrees, if you remember, we talked about this in physics 1, it actually shrinks when the temperature goes up, okay? And then the other way around as well. In some bridge structures, you'll see these gaps over here between two pieces of segments. So that is again to prevent cracks happening due to the thermal expansions of the concrete. Okay, so if over time you might expand if you don't have this kind of gaps in between. So mathematically, we'll write this. So delta L stands for the expansion of the material in length, and then L is the length of the material originally, or L naught, either way. And that should be equal to a constant called alpha times the change in temperature delta T. So alpha is a constant of expansion for materials. You can rearrange, so alpha is delta L over L divided by delta T. Okay? So this alpha is called coefficient of linear expansion. So we are just looking at the expansion in one dimension. So SI unit for this alpha is actually Kelvin inverse. You can see from the derivation over here. change in length will be in meters as a unit, and this guy will be in meters, but this T will be in Kelvin. Now, Kelvin, change in temperature in Kelvin, if there's a 5-degree change in Kelvin, that's the same as 5 degrees in Celsius. So then you can also use Celsius inverse, okay? So these two are the same when we are talking about change in temperature, delta T. All right. So if you need coefficients of thermal expansion for certain materials, you can come to this table. For metals, they typically have larger coefficient of expansion than other materials. Okay, so lead is 29 times 10 to the minus 6, 24 times 10 to the minus 6. Although these are larger than other materials, but all these numbers are actually pretty small because they are all multiplied by 10 to the minus 6. Okay. You see concrete, glass, and then quartz, they are smaller than those metal materials, although some are getting closer. Okay, but for those lead, aluminum, and brass, they are larger than the others. The original and the old-fashioned of thermometer, if you see like this one, if you find somewhere in the building, it's actually using the expansion, the difference in expansion of two metals here. So there's a bimetal strip made of two metals here, and because of the different coefficients of expansion, so it depends on temperature. So if you have lower temperature, it will bend to one side because this lower part will expand more than the part the upper part A, or in the other case, if it's hot, then A will expand more than B, or actually A will shrink more than B, so then it will bend to this side. Okay. All right. Now, materials also can expand in two dimensions. So if you just look at one dimension, let's say in the X dimension, then you have that expansion. If you look at the Y direction, then you also have the expansion in Y direction, okay? So if you have a 2D materials, it will expand both in X and Y. Now, if there's a hole here, it will actually expand, and the hole will become larger in that case. For 3D materials, it also will expand in the all three directions. So X, Y, and Z direction, they will also expand in that case. We'll take a look at the two-dimensional expansion. And for two-dimensional expansion, so you will have expansion in area. So delta A, that is about twice of 2 times alpha times A times delta T. Okay, so this 2 alpha then is the two-dimensional efficient coefficient. Okay, so let's say if we have a square material, let me switch my camera. All right. So if there's a square material, and if it expands, so the two-dimensional, so it will expand in X direction by this much, delta L. The original is L, okay? And then in Y direction, original L, it will also expand by delta L. So now this material becomes this guy. So the expansion part then will be this, okay? So the amount of expansion, then it should be the area of this guy. So we will do delta A, it should be A prime, the area after expansion, this whole thing here, right? Minus the original area, okay? Now we know original area, A, is just L square. Now after expansion, A prime is L plus delta L, right? N squared. So this is like A plus B squared will be L squared plus 2L delta L plus delta L squared. Okay. Now in one dimensional, delta L is equal to the alpha times L times delta T. Okay. So delta L compared to L is going to be a small number because this guy is typically, let's say, times, if you remember, it's something times 10 to the minus 6, right? So let's say if it's 20 times that, it's still a small number. Okay, so compared to L, and then temperature change, let's say maybe 10, 20 degrees or whatever. So still delta L is going to be much smaller than L, okay? At least in the thousands, hundreds of thousands of smaller than L. So in that case, delta L square then is going to be much smaller, okay? So compare this guy and this guy. This guy is already small compared to this one, and then this one is even smaller. So this is called higher order of approximation. So these ones you can actually basically ignore those. So then A prime is going to just approximately equal to A L squared plus 2L times delta L. Okay. So then A prime minus A will be just L squared plus this guy, L squared plus 2L times delta L minus L squared. Okay, approximately equal to that. You see L squared and L squared cancel. So then this is 2L times delta L, which delta L is equal to that guy. So it's 2L times alpha times L times delta T. So L and L becomes L squared. So you can write 2 alpha L squared times delta T. Now L squared is A, the original area, right? So then this is 2 alpha of A delta T. Okay. And this is exactly what this is equal to delta A, the change in area. Okay, so in the PowerPoint slide. So let's go back to the PowerPoint slide now. And we going to share that. All right. Now you can also oh, just quickly emphasize this. So delta A change expansion in two-dimensional is approximately twice of alpha times the original area times delta T. Okay, and so basically area expansion coefficient should be 2 times our linear expansion. Similarly, you can show that for three-dimensional expansion, which is called volume expansion, it's going to be 3 times our alpha of the linear, and then times the original volume. So beta is 3 times alpha times the original value times the dot t. Okay, in that case. So changing volume, which is volume expansion, is equal to 3 times alpha times v times delta t. And this is again what I mentioned. Water is actually a pretty weird material. So it actually, the density of it actually increases when the temperature goes up in this range, okay, 0 to 4 degree, because normally material will have volume expansion when its temperature increases, which means temperature should decrease. Like on this side, this is normal, but in this side, it's a little bit weird, although it's small. All right. Now, application of thermal expansion. So right now it's cold most of the days it's cold outside. So then if your gas tank says now empty, you actually go further because the volume of gas actually shrinks. So for the same amount of the volume of gas, you actually have more gas totally molecular-wise or in total mass-wise is more. So you have more gas molecules, and actually you can go a little bit further. Okay, but I would say as soon as your gas tank hits low, find the nearest gas station to fill it up. Anyways, okay. All right. So, but if you have the choice, it's probably more economic to fill your gas tank in the morning than in the middle of the day because temperature tends to be cooler or lower in the morning compared to middle of the day. So you actually, for the same amount of gallons you are getting, you're actually getting more gas in the sense, or more number of gas molecules in that sense. All right. So we'll take a look at this last example here. So this one says early in the morning when the temperature is 5.5 degrees Celsius, gasoline is pumped into a car's 53-liter stainless steel tank until it's filled to the top. Later in the day, the temperature rises to 27 degrees Celsius. Since the volume of gasoline increases more for a given temperature increase than volume of the steel tank, gasoline will spill out of the tank. How much gasoline spills out in this case? So this one does not necessarily refer to your um, um, well, let's put it this way. This one it's assuming that you're not driving, you're not consuming any gas. Okay, so in that case, so it might spill out a little. Um, so it gives you all this coefficient of linear expansion for the metals. So the gas tank is made of steel. So you'll be looking at steel here, which is iron. So you'll take this as the coefficient of linear expansion. And then for the gasoline, it's giving you coefficient of volume expansion. So be careful about if you are given linear or volume. So this side is volume, so then you can use that. But this side is linear. But when the gas tank made of steel expand, you're going to use its volume expansion, which means 3 times of these numbers. So for steel, you'll do 3 times 12 times 10 to the minus 6, which is 36 times 10 to the minus 6. Okay. All right, so let's take a look on this one. We'll start with, so how much it spills. So then we'll be looking at the expansion of gas tank, right? So this is beta times original times delta T. So that's expansion of gasoline. Let's say delta V of gas, which will be beta of gas, right? Times V of gas originally times delta T. And for the tank, so V of tank should be beta of tank, which is steel, times V of steel originally, times delta T. Okay, so the change of temperature should be the same. Original volume of gas and tank should be the same. Let me just stop sharing so then you have a better view here on my work. So these two are the same. So imagine if there's a gas tank, right? Let's just say it's a cylinder, and as temperature increases, this guy will expand a little bit, right? So it expands a little bit like that. And then when the gasoline expands, it expands a little bit more because it has larger volume expansion coefficient. So it may become like this. I'm exaggerating over here, but you'll see this guy now is bigger than this guy. So in that case, so you can either do the final volume of the two minus each, subtracting each other, or you can just do the the expansion part minus that, right? So you can do the just expansion part of the gasoline minus the expansion part of the tank, okay? So the amount of spill then, delta RV spill, then should be equal to the amount of gasoline expansion minus the amount of tank expansion because gas expands more than tank, okay? So this would be beta of gas, V, because these two are the same, I'm going to just use V and delta T, okay? Minus beta of steel times V times delta T. So these two are the same. So it's basically beta of gas minus beta of steel, and then times volume times delta T. This is original volume, okay? So delta V of spill is beta of gas minus beta of steel times V times delta T. So this guy, as given in the problem, is 0.95 times 10 to the minus 3. And this guy still is given as 12 times 10 to the minus 6. But it was given at was alpha, not beta. So you do 3 times that, okay, for beta. Times the original V, which says it's 53 liters. And then times the temperature change, it says in the morning is 5.5. And then in the day is 27. So that's the difference of the two Celsius in Celsius. So remember, if you are doing delta T, you can either doing the difference in Celsius or in Kelvin, okay? You can convert then those two temperatures in Kelvin and then subtract them from each other, it will be the same. Because both you are just adding 273.15, okay? To those two numbers. So at the end, you'll get about 1.04 liters, okay, of spill. So that means if you fill the gas tank in the morning, you get about 1 liters more than if you are filling the gas in the middle of the day. So compared to this, yeah, it's a little bit almost like 2% more of gas you are getting. Okay. All right, so I hope you learned something today that you can apply now to your daily life. Don't worry about the spill of actually it wouldn't the gas tank actually has room for that. Okay, so at least it never happened to me. Okay, all right, so that will be it for today. I will see you guys next time. So remember to try the homework, and then I would prefer you guys actually try that before the class. And then bring your question to the class so we can work on it together. You can have discussion with your classmate. Okay. All right. See you guys next time.